Okay, suppose that A1 is negative 1, 1, 1, and A2 is negative 1, negative 1, 1. Then, find one linear combo of these vectors. Okay. What's a linear combination? Scalar and vector. So let's go ahead and define the vector B. What would B have to be if B is a linear combination of A1 and A2?
A1 plus A2.
Okay, what's the easiest scalars you could think of?
1.
Yeah, okay. 1 times A1 plus 2. Whoa, that's fancy. Times A2. This is 1 times the vector negative 1, 1, 1 plus 2 times the vector negative 1, negative 1, 1. Okay, 1 times that vector? Yeah, well, it's Wednesday, so that must be like that. What about that? 2 times that vector? Okay, so what is B now? B must be negative 3, negative 1, 3. Can I tell you something? You just solved a matrix vector multiplication problem. The matrix would be negative 1, negative 1, 1, and the vector would be 1, comma 2. Was that, do you think you could do that? Okay, we'll get there. Yeah, go ahead.
1 and 2 as our scalars, did we have to take them from a set of...
What's the only condition on our scalars? Where do those exist? In R. So what's the only condition I have on my scalars?
That they're real numbers.
That they're real numbers. Shall we look at another linear combination? Perhaps we'll call this linear combination 1. Shall we take another one? Let's take another linear combination. Let's call B 2. Can someone give me another linear combination of those two vectors? Peter, perhaps?
2, 1.
Can you give me something exotic like a negative in there? Ah, there we go, Peter. Yeah, negative 2, positive 1. All right. So here we go. Now we go negative 2 times negative 1, 1, 1 plus 1 times negative 1, negative 1, 1. What's this? Positive 2, negative 2, negative 2 plus negative 1, negative 1, 1. What is the vector B? 2? 1, negative 3, negative 1. Could you guess how we would write this as a matrix vector multiplication? I don't care that you know this right now, but the reason that I want you to study matrix vector multiplication is so that we can preemptively make connections between the theory that we're building and the problem that we want to solve. So that instead of waiting till after you get the information to be like, oh yeah, that's what we're doing, that you can actually build intuition about what you're doing in the major problems of linear algebra while you're learning the underlying theory. What's this theory called? What is it called when I take a scalar times a vector plus another scalar times another vector? Linear combination. What is every linear combination? Give me a V, V. Give me an E, E. Give me a C, C. Give me a T, T. What does that spell? Vector. Every linear combination is a vector. How do I form that vector? What do I need? You're having fun, huh? Either that or I just don't understand. How is this guy so excited about this? Well, make a few $100,000 on this material. And then you'll figure it out. And then realize, like, the way I always think about it, we have some major problems in our society right now. We have something called global warming. The current politicians that are in power, they're going to be dead when we're dealing with the heat on this planet. You know who's going to deal with that, really? It's going to be my sons. The reason that I think a lot about this is, do you know what most mathematicians do in their classes? They make everybody in their class feel like they can't do math. That's the feeling I got in every single one of my math classes, that somehow, no matter what, no matter how hard I worked, there would always be stuff that I couldn't do. And you know the opportunity cost of that, in my opinion? It means that when we're in math classes, stuff that could be brought to bear in ways that we've never thought about it, the people that have the most potential to make future changes believe for themselves that this stuff is useless. Anybody ever finished a math class and thought to yourself, well, I got an A, but What the hell am I going to do with that? In my opinion, that's a failure of the system. If this system was designed well, if I design my classes well, if I show excitement out of this material and actually empower you, my claim is you all may use linear algebra in ways that I've never even dreamed of, and you may bring linear algebra to bear on problems that literally will change the world in the future. But in order for you to get to a position where you think that you can do that, and then you actually spend the time to do that, I have to inspire you. If I don't believe in this stuff down to my core, how am I going to inspire somebody else? I'm very serious about this. This stuff, like linear algebra, literally, I believe that any problem in math that you want, map it back to a linear algebra problem, you're done. Like this is like a Roman keystone. You know what a Roman keystone is in an arch? You take the keystone out, guess what happens? The whole thing collapses. If I took numerical linear algebra out of the world at this instance, planes would fall from the sky, that camera wouldn't work, our entire world would end, right? In the way that we know it. We'd go back to like making fires, right? Yeah. What's a linear combination? A vector. What vector is it? It's a scale. It's a combination. It's a combination of scalar vector multiplication and vector addition. In order to define a linear combination, what do I need? Now I want you to bring in the matrix vector multiplication problem. What's the matrix vector multiplication problem? A in m by n. So now I have n vectors, each of which are of size m. What else do I have? A vector x. Vector x in size Rn. What does it mean to have a vector x in size Rn? It means I have n scalars. So I have n vectors and n scalars. In a linear combination, what do you know about the number of vectors and the number of scalars that I have? Identical. The number of vectors must be equal to the number of scalars. If I have the same number of vectors and the same number of scalars, how do I form a linear combination? First scalar times first vector. Brrr. Nth scalar all the way down to nth vector. Now I get a bunch of vectors that are scalar vector multiples. What do to them? I do a bunch of sums. What's that sum called? Linear combination. What's a linear combination? A vector. What vector is it? Scalar vector plus scalar vector. How many of those summands do I have? N of them. Each summand is of size m by 1. Question: how are linear combinations related to matrix vector multiplication? Do you know I've had people who are in linear algebra classes that I was helping teaching and got A's in those classes, and at the end of the class they could not say that sentence out loud? You laugh. This happened at UC Davis and at UC Santa Barbara. At my time in UC Santa Barbara, I got one of the highest grades in my linear algebra class. I could not say out loud that matrix vector multiplication was a linear combination of the columns of the matrix A with the scalars coming from the vector x. You are now more advanced in the first 3 weeks in this class than I was at the end of actually 4 linear algebra classes, including 1 lower division and 3 upper division classes.